Okay, for homework 10.5, we're opening up the PhET bending light simulation. Material B becomes your top material, and air becomes your bottom material. In this case, I'm adjusting the incident angle. That would be the angle that your ray of light makes with the normal line, and I'm going to adjust it until I see the critical angle. So, when it's below the critical angle, my light ray would look something like this. It goes in towards the boundary, bends away from the normal line because it's going from a slow material, where light is slow because there's lots of particles in the way, to a fast material. It bends away from the normal line, making a larger refracted angle in the faster material and a small incident angle in the slow material. Now, if our angle is anything below 46 degrees, I see that my diagram looks something like this. If it's any angle above 46 degrees, let's say 50 degrees, then what I found was this. Light goes in towards that boundary, but instead of passing into the air, light bounces off. It refracts so hard back into the original material that it doesn't go into the air at all. And guys, even though this is called total internal reflection, that's kind of a misnomer. It's not true reflection because we know that air is not a reflective material. In this case, these two angles are equal because they obey the law of reflection, but it's really from refraction at large angles when going from a slow material to fast. So the critical angle is something in between this. It's the angle at which it doesn't stay in the air and it doesn't go back into material B. The critical angle is going to be the special angle at which when light goes in this case, we measure the critical angle to be about 46 degrees in this simulation. Then it goes right along this air material boundary so that my refracted angle is 90 degrees. Okay, so my critical angle is 46 degrees, so that means anything below 46 is just regular refraction. If you put this in the simulation, it works too. I get just regular refraction at 27 degrees. Looks just like this, actually. At 46, you get the critical angle. And at 80 degrees, you get total internal reflection. So let's use the definition of the critical angle to calculate the index of refraction for material B. In this case, we're going to use the ni sine theta sub I, that's our Snell's law, knowing that that product stays constant as it travels from the incident to the refracted material. The incident material is material B, and that's the index I don't know, so I'm going to leave that blank. Maybe you put a little circle around it. I know that incident angle is 46, so at the critical angle is 46 degrees. I put that in for the incident. Air is the refracted material, and notice that air's angle is 90 degrees at the critical angle. Sine 90 is 1. Sine 46 with your calculator in degrees is 0.72. And I'm going to divide by both sides by 0.72 to get our index of refraction. That would be our 1.39. And just to double check for sense making, index of refraction should be a number between 1 and about 2.5, and it's unitless. So that's good. Now, try this in the simulation. If you switch material B with air, you put material B on the bottom and air at the top, it turns out this doesn't work. Or it does, but it never ever gives you total internal reflection. And the reason is, let's say I make it at a really large angle. 80 degrees was certainly above critical before. If I go 80 degrees, so really, really steep, light going from air into mystery material B, it always bends towards the normal instead of away from the normal. And since the refracted angle is always smaller than the incident angle when it goes from fast to slow, it bends towards the normal line instead of away from it and never gets trapped in the air. In order to have total internal reflection occur, it always needs to be going from slow to fast, not fast to slow. So now back page, moving right along, we go measure the critical angle one more time. But this time we're looking at material A into air, and it's a little bit hard to see in the video. So this is light going from material A into air. But when it goes towards the air, it bends away from the normal line so hard that it travels along that material air boundary, making the critical angle and the incident angle. Now this time, notice I listed a bunch of things. Incident ray, that's this one, the ray that goes where the light originally was. The refracted ray, that's this one. The incident angle is the one between the incident ray and the normal line, and the refracted angle is between the normal line and the refracted ray. And as closely as possible, this critical angle is something like 25 degrees. Now that is really low. Most of the other critical angles that we've dealt with are in like the 40s or 50s, so this must be a really special material. So let's try this again. For me, it always helps to write out the equation instead of trying to do this one off the top of my head. And the reason I suggest that is because I have two indices and two angles. And if I don't match them up correctly, then I don't solve the problem right. So I'm trying to find mystery material A. That's the incident material. And I know the critical angle was 25 degrees. I know it's going into air, so the refracted index is 1, and that's sine 90. Since sine 90 equals 1, and sine 25 gives me 0.42, I'm going to divide both sides by 0.42, so that Ni is equal to 2.37. Now, that number is special. That's really, really high. This is most likely going to be a diamond. A diamond is the index of refraction that is closest to this N. And guys, one of the reasons diamonds look so shiny and beautiful and we like them is actually because it has a very high index of refraction. Because it has a very high index of refraction, light gets trapped inside very easily. Any light above 25 degrees does this total internal reflection thing, making all of its surfaces seem to glitter and glow. And we don't see it as straight reflection because normally diamonds are so small. Plus, with dispersion, the breaking of light up into its component colors that occurs with refraction, well, diamonds not only look shiny and pretty, but you also see different colors of light in them. Cool. Okay, which leads to the last bit, this fiber optic cable. I'm going to take my index of refraction of lucite and use it to calculate the speed of light. The speed of light in lucite is 3 times 10 to the 8th over 1.5. That's 3 over 1.5 times 10 to the 8th, and that gives me 2 times 10 to the 8th meters per second. Now this one asks you to go backwards here. Calculate the critical angle. And off the top of my head, let's just sketch here. The critical angle for lucite would be the angle from which it's going from lucite into air. And so I'm trying to find this theta I right here. I'm trying to find theta I such that the refracted angle is 90 degrees. So that's Ni sine theta sub I equals Nr sine theta sub R, where Ni is Leucites, that's 1.5, sine something, I don't know, is equal to 1 sine 90. So I'm going to divide by 1.5 on both sides. Remember that 1 sine 90 is 1. So the sine theta is equal to 1 over 1.5. Then I would want to take the sine inverse of both sides. So I'm taking inverse sine of 0.66. Theta I is inverse sine. Make sure everything's in degrees in your calculator mode. And that gives me back my 41.8 degrees. Finally, what does this actually mean? Like, what do we use this for? Well, we use this for transferring information. Because this means if I put a laser on one end of this tube and I send light down, when light hits this normal line at 60 degrees, that is above the 41.8 degree critical angle. And so my green light would travel at 60 degrees until it hits the next boundary. Notice it's obeying that law of reflection here. At the next boundary, it hits at 60 degrees, which is still above the critical angle. So it does total internal reflection again and travels all the way down this line. So it might hit a normal line several times until finally it leaves the tube. We can use this to send signals at super quick speeds, even through things like the ocean. So, how long would it take to travel 3 million miles? I'm saying ignore the vertical movement, the like it goes back and forth and back and forth and back and forth. Assume it's just moving 3 million miles laterally. Well, this equation's asking for something to relate a time, how long, to a distance. So I'm going to use my definition of speed. I'm using the speed of light through the fiber optic cable, not the 3 times 10 to the 8th. So this is 2 times 10 to the 8th equals 3 million miles. I meant to say meters. You'll see that. 3 million meters. My bad. And solve for t. Multiply by t on both sides so that I have 2 times 10 to the 8th t equals 3 times 10 to the 8th, 3 times 10 to the 6th. Divide by the 2. And so I get a fraction of a second here. I get 1.5 times 10 to the negative 2. Or how I would commonly write that is 0.015 seconds. So we use fiber optic cables to actually send signals of light, not signals of electricity, across huge distances at very rapid speeds. Not only that, but if I wanted to send several signals at a time, I could make one laser sending a green signal, one sending a red signal, one sending a blue, and they won't interfere with each other because they're different wavelengths. Very, very cool. All right, so best of luck to you all. As always, email with questions.